Hi, so welcome to week 5 of the online course on Combinatorics 2 at Stockholm University. And so we will, this week we will talk about partitions and exponential generating functions. So it starts with partitions. So if you think about partitions, you always have to be a little careful here, whether you mean ordered or unordered partitions, and but often they have different names. So the ordered partitions in the book they are called compositions. So the ways to write a number, a positive integer, are as a sum of positive integers where the order is important. So this is something we actually have already seen. Now, for instance, what I mean by this, for instance, 9, you can write it as well, 4 plus 5. But you can also, in many other ways, you can also write it as 5 plus 4. And so we consider these to be two different ordered partitions, so two different compositions. And so how would you count, for instance, the number of compositions are in two parts? Okay, so, well, this is not so hard. This is the number of solutions, well, yeah, integer solutions. So the number of integer solutions to the following equation, r is equal to x1 plus x2. Where x1 and x2 are integers, greater or equal than 1. So we're going to solve the equation r equals x1 plus x2, so different, distinct, and x1 has to be at least 1 and x2 has to be at least 1. And so, well, we already know how to do that. This was the whole business of generating functions. And so this is something which is not too hard. And so have a look, for instance, also at example 9.12 in the book, which talks more about compositions. Okay, so, but this is not really what I want to talk about, but I think it was important to, kind of contrast it to what we want to talk about now, maybe partitions. And so partitions really means unordered partitions, so the order is not important, so let's just write it down. This is a number of ways, so these are ways to write positive integer r, non-negative integer, as a sum of positive integers where order does not matter. Okay, so for instance, here, so while previously these two were considered to be different, in this case, the composition 9 equals 4 plus 5, and, sorry, the partition 9 equals 5 plus 4. So these two as partitions, these are really the same. So they are only counted once. And so P of R is defined as a number, the overall number of partitions of R. Okay, so these are all the partitions in no matter how many parts. And so the interesting thing is that there is no nice formula for this. So you get a sequence of numbers and you might think maybe there's like a nice recursion formula or something. But, well, not really. It's kind of a more complicated thing. That's really what makes things more interesting here. And so let's look at an example. So let R be equal to 4. And so how many partitions do we have in this case? Well, we have 4 itself. We have 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and finally 1 plus 1 plus 1 plus 1. And we see here we only count, for instance, here we only count this once. So the answer is that P of 4 is 5. Now this is easy in this small case to figure out, but what about if you have some really large numbers? And so in order to deal with these kind of questions, make this more systematic, so there's a trick. How you can do this. Namely, we use some new variables, let's call them y, so y1 and so forth. So y1 we define as a number of ones in the partition. And y2 would be the number of 2's in that partition. And so forth. So we don't, like previously we had order, so we could say, well, we can count how many balls you put in that box or in that box. But now everything's kind of, because the order doesn't matter, it's not really clear. But what we still have here is we can, now, so what you do is to do something a little bit different. We now count the number of ones you're having, the number of 2's you're having. So, in which way does this help? So I claim the following. I claim that that P4, so the number of these partitions, is equal to the number of solutions of the following equation. And let's again put in a non-negative number of integer, non-negative. And maybe I find some colored chalk here. There we go. Okay, so here's a new equation. So this kind of, it looks different because previously we never had any coefficients in front of the variables. So in this case, we have like 4. So how can you why is this true? Why does every partition satisfy this? And maybe you already see it. But it's just, look at this here. We had like the partition 4. Partition 4, essentially you should think about it as being, well, there are no 1s, no 2s, no 3s, so there's only 1 4. So it really corresponds to this. Well, here we have 1, but no 2, but 1 3, but no 4. Here we have no 1, but we have 2 2's, no 3, no 4. Here we have 2 1's, 1 2, no 3, no 4. And finally here we have 4 1's. And now we can just check that, well, this satisfies this equation. So 4 plus 0 gives you 4. For instance, here you have 0 plus 2 times 2 plus everything else 0 gives you 4. And so I think by now you should see why this holds. You just count the number, for instance, how many 3's there are. Of course, you have to count each 3 3 times, because so in order to sum up to 4. Okay, so it's not really kind of difficult to understand, but it's really a nice trick, because somehow we're now thinking differently about this. But now we again get an equation where we have some order. We can now use, somehow we are now back in the realm of things we already seen before. So this shouldn't look so complicated now. So now finally we now have something we can maybe deal with. And so let's solve this problem. So this will be the coefficient. And let me maybe just write this first. X to the 4. Okay. Okay, so let's look at this. So if there wouldn't have been any coefficients in here, we wouldn't have known what to do. The only restriction here really is, what do we have for restrictions on the y's? Well, it's that it's non-negative. So if it would be all here would be just of 1, it would be 1 plus x squared plus dot 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 times 1 plus x squared plus x to the cubed plus dot 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 and so forth. So we would have gotten 1 over 1 minus x to the 4. But now we have these coefficients in here. But if you think about it, that just means that we have to take the corresponding power here. Okay, because so here we take the powers of 2, so x to the 0 plus x to the 2 plus x to the 4 plus x to the 6. Here we take the powers of 3, 1 plus, so x to the 0 plus x to the 3 plus x to the 6 plus x to the 9 and so forth. And here the powers of 4, 1 plus x to the 4 plus x to the 8 plus x to the 12 and so forth. Why? Because if you now look at the coefficient of x to the 4, how do you get that one? Well, you pick monomials in here. And for instance, you could take, so let's see if we can maybe get the 2, 1, 0, 0. Well, in that case, how do you get that one? We have 2 1s. So we take the x square in here. But you only have 1, 2. But the 1, 2, of course, comes now with the factor 2. So we should take x squared to the 1, which is x squared. And then the other ones are 0, so it's x to the 0 and x to the 0. Or maybe let's take 3 plus 1. That corresponds to 1, 1 and 1, 3. And no 0, 2 and no 4. So this is that solution to that equation. And that corresponds to taking, well, to taking like 1, 1. So to take this x, no 2, so we take just the 1. But we have 1, 3, so it's x to the 3 to the 1. So we take this guy. And then we take just x to the 0, because there are no 4s. And so forth. We can just look at all of this in this way, and therefore this is just the coefficient of x to the 4 in this equation. And so, well, expression, more appropriate. So this is 1 over 1 minus x. Now what is this? We already had that one. Think about substitution. This is like x squared to the 1, x squared to the 2. So this is 1 over 1 minus x squared. This is 1 over 1 minus x cubed. And this is finally, and maybe I should write it appropriately, like here. And so what we get is a very easy description in terms of generating functions. If you write them as quotient of polynomials, it's very easy to remember this. And so this example really works like in general. This is just like how you do it. You can do it for other r's, of course. And so this is something important here to remember. Okay, and so as before, when you're talking about generating functions, the questions can be a little more complicated. You have to modify these problems. So you should try to do the following. So now what if you want to count only the number of partitions of 4 where 2 is the largest summand? And what if every summand should be at most 2? And what if 2 appears only once or twice? In which way would you modify this generating function you've seen before? In which way would you modify this? This is something you should think about. So there's something more about partitions. This is called the Ferris graph. It's really nice. It's very simple, but very useful. So for instance, let's think about something a bit larger. So we see something going on here. So 4 plus 3 plus 3 plus 2 plus 1. So this gives us hopefully 13. And let's do this graphically, meaning so I claim that this should correspond to, okay, so we have 4 here, so we write 4 dots. Now we have a 3, so 3 dots. Another 3, so again 3 dots. 2 dots, and finally 1. That's another way of, that just precisely corresponds to this, just written in a more like a pictorial way. And now what you do is, so we just flip it. Okay, so we just flip this. So just flip this. Well, maybe that's, of course we don't flip like this, but now this corresponds, so let's write like this. So now flip. Or transpose, if you know about matrices, that's the way what we really do. So we transpose this. So that 4 comes down here. Or here, 3, 2, 1. Okay, but now again we can, so after doing this like previously, horizontally, now vertically, now we can again read about this horizontally. And so what do we get? We get 4 plus 4. Wait a second, there's something wrong. Probably you noticed, yeah, this is like 5. 1, 2, 3, 4, 5. So 3, 3, 2. I forgot about the 1 here. So, okay. Again, okay, so we have 5 here. So this is 5 plus 4 plus 3 plus 1. And, well, we get 13, of course. Why? Because we have the same number of dots here. And now what we see is the following. We see that from each partition here, we get another really different looking partition there, and vice versa. So this is what's called a bijection. This means that if you count, so it's kind of 2 ways of going through these partitions. If you go through them one way, or you can go through them by looking at the transposes. Same thing. And so why is this useful? Because of the following observation now, that the number of partitions of R in n summons okay, assume we want to know the number of partitions of number R in n summons. I claim that this is the same as the number of partitions of R where n is the largest summand. The largest part. The summand or part is the same thing. So what does it mean? It means that every of these parts is at most as big as n, but there's one which should be equal to n. And so why is this the case? Well, for instance here, we have, in total we have now, how many parts do we have? 1, 2, 3, 4, 5. We have 5 parts, which means that we have 5 rows. Now flipping this gives us 5 columns, where the first one, see here, the first one goes all the way down, so it's length 5, so this one is also length 5. So what we see, well, in this case, the largest part here is 5. So it means like when we go through them and we look at all the partitions in n of R in n summands, it's the same thing as just by going over there, as counting the number of partitions where n is the largest summand. And why is this so useful? Because that question here is not really clear how to do it using the previous example, but using this observation, Now we have just to count the ones where n is the largest summand, and that's something we were just talking about. And in the homework, for instance, there was such an, where is it here? There's such an example. So this is easy to do. So that's harder, but that is easy. And using this observation, you can relate them to each other. And so please also think about this, what this means if you're counting at most n summands. In that case, this also works. In that case, the number of partitions of R in the most n summands corresponds to the number of partitions of R where every summand is at most n. Okay, so finally, now we're in the position to talk about the big table of counting. So this is table, so you find this in the book as tables 5.13 and 9.5. So these are all in that supplementary sections. Okay, so this looks pretty impressive probably. Now here's the problem we're looking at. So the problem is the number to count the number of ways to put R objects in n containers, so in n boxes. And now we have lots of, now this question is vague, as we know about this by now. It depends on whether the objects are distinct or identical. So here the first four cases when the objects are distinct and then if they're identical. But now there's one more thing. Maybe the containers could be also distinct or could be identical. So again, they have now to distinguish between distinct, identical, distinct, and identical. And finally, we have a third option, namely the question is whether you have to put a ball into one of these boxes or not. So can the boxes just be empty, or do all the boxes have to be non-empty? And so here's the answer to that, either it's yes or no. And so we have for each one 2 possibilities, so we have 8 possibilities, so 8 in total we get these 8 rows. Now for each one of those, by now we know how to do them. And I won't go over all of these cases again, so this is something you should do. You should know all these first 6 cases is something we already talked about. And so you should make sure you know why these are the answers. So this is very important. If you feel very competent with this table, you will do very good on the exam. And so these are the first 6 cases we already talked about. So try to understand them, why these are the answers. And the new thing we had are just these last 2 ones. So if you have identical balls and identical containers, boxes, so think about it, you have these boxes here all look alike, you put in the balls, now you have like maybe 4 balls, maybe put 2 of them in one box and 1 in another box and maybe, in another box. And so kind of this is precisely corresponds to the partitions of the balls. And so the number of partitions of R into at most n summands, because you have at most n boxes you can put this stuff in, and depending on what you get all these different kind of partitions. So again, think about this a little bit, like really convince yourself that this is true, that this is really the same, that this is really the answer to that counting problem. And now if you don't allow the boxes to be empty, if you have to put something in each of the boxes, it means at the end we have to have n summands. Because you look how many are in this box and how many are in this box in total, but of course the order doesn't matter. So we'll get precisely partitions, but we have to have n summands because we have to use all the n containers. And so these are the 2 problems, again, that we're just talking about. And so please have a look at this. This is very important.